Okay, maybe we give it a start. Just to, first of all, a big excuse for starting this as a video. I have received feedback that you don't really like that. What I promise is that we will have all the lectures in presence over the term, and I will offer, especially at the end of term, something, and also in preparation of the exam, something which is all live, and I will make sure that this is happening. We have the first session, as I announced, which are different, but I just would like to make sure that you understand that I don't like this, and it's just because I was forced essentially to do this that we start. I wanted to start today to give you a kind of overview and introduction, that we get into some rhythm here, and that's what I want to do today. Maybe I introduce myself. My name is Rüdiger Quay. At the moment, the director of one of the Fraunhofer Institutes here in Freiburg. I will talk about this in a minute, and we are also at the chair of energy efficient high frequency electronics, which is mostly devoted to energy efficiency and resource efficiency in the microwaves, which is something I also will put into this lecture, that you see also some new ideas which are constantly being refreshed, and especially for the microwaves communication, strong changes are happening due to the resource. And then also this lecture will have really a lot of new items in the regarding the things we are researching on in the direction of sustainability. I gave you a script, which you may have downloaded already, that contains some content. There will also be an update at the end of term. It's anything which is changed in the lectures will be also given in an update. So there's nothing which you could lose or in any way not have. So let me start this. So first of all, the dates. So just for everyone again who's here. So today we have a Teams. It's live. Next week we will have a little video, no lecture live, and then the rest will be normal. What is something we always do, and which is quite nice, is the Christmas lecture, which is just before Christmas. This is the holidays at the end of the year, depending how you run this. And we always have that live, and also with a special dedication, which is always a great thing to be there. And I hope, despite of some of you leaving for home, maybe we will be there. So that's something I always like. I just need to put people in, because otherwise they don't see anything. What I also would like to mention is that a few people like to join later, no problem. Just make sure we get them in. Very nice. So this is the plan, and there's a script which you can download on Ilias. For those who made it here, they actually should have received the password, but it's microwave 22 in small letters, and then you can actually access Ilias, and you will find it. We'll be going to Fraunhofer. For those who haven't had a chance yet to do that, we will have a special session there where we were showing you the clean room and also the things we are doing. It's at the end of term, and probably because we are missing out the next lecture, I will also give you an invite to visit before that we have some live things at Fraunhofer, which will also be a bit more interesting than just sitting in the lecture room. So I've thought of something. So interaction is critical. At the moment, I'm again playing on oral exams. For the other lecture, we did a written exam. At the moment, with the present expected number of people in the oral exam, I would probably try oral again if it's completely out of range, because you're too many, and last time it threatened to be over 65 people taking the exams, which didn't happen in the end, but that was something. I cannot do 65 oral exams. But here, I think we will try again, and that's probably what we're gonna play. For those, just to remind you, there was the indication intermediate. There was this idea that the first two lectures in 23 would be skipped or in some way online. This is not happening, so we will be live and there, so in presence. Just to remind you that, because you heard that the university recalled that and said we're gonna do it very normally, and I think that's a good thing. And we might also put some additional dates, and I will ask you for some availability when we have another session here somewhere, what would be a good thing, and we will also see in the room whether how we play this. So that's something I'm gonna announce later. Yeah, so you found the Ilias. This is just the wrap up here. If you haven't found it, that's just what we're gonna do, and you can see this. And this lecture is on circuits and systems, and then and before we come now, what we are going to talk about is just to remind you, it's as I said, everything is recorded, so you can do that. I like that people have the opportunity to do videos. What is a threat of videos is that if you have never heard it and then pile up 15 videos of 90 minutes, which you have to listen to, that normally then typically doesn't happen. So it's not good in the sense to pile up this stuff. But if you want a special report on a specific topic and want to rehearse it and look at it again, so then the stuff is at least available. Okay. Yeah, this is circuits, and there's always something I like very much, which is there's quite a universal circuit simulator which you can play with, and that's available. So that's quite nice, and then it's one which we are always using. And if you have some fun in this, you can also try that. Some people like software, and there's good examples of what we are doing, and you can actually try, and it's for free. It's open source, so it's very nice. It's available on all the machines, so you can download it here as given here on sourceforge.net, and you can just play a little bit of the stuff we are doing, because it's in. And there's also the exercise related that I'll come to that, but this is something you can now do as we speak. Literature, I'll come to this later. Maybe just to make the distinction. Some people have taken the exercise in 22 already, and some people are going to take it in 23. And this is related to both of them. Officially, it is related to the left one, the one we are just having. And however, I don't force you into an order, because my personal feeling is your stuff is already complicated enough. Your schedules, you have to study a lot, and I don't want to keep you from doing something useful. So if you want to do it in any order, I'm fine with that. And you can learn, and you can get forward in the order that you would like. And there's this clear distinction what we are doing here. So this is system related, and this term we will focus even more on systems, while here this is more semiconductor related, and we also look at the devices which are being used. And I think it's good, because the knowledge which is given here is very useful in industry. People ask for jobs extensively. Industry is needing you very urgently, and we just have to get you there and give you the appropriate knowledge. So that's something I can definitely say. Yeah, and what is very interesting here is that we have a very nice mixture. So some of you may have already had the design course or the exercises in the microelectronic, which is analog design. Maybe I can look at you a bit. Who has been in the lectures from the chair of former Manoli, now Mr. Kuhl, and Mr. Related to the microelectronics, Mr. Keller? You don't have just that I have a feeling a bit what you know already. That's important, because so it's a good. There's some people showing up. I like that. Oh, it's like a Christmas tree. Very nice. Yeah. And the good thing here is what you need to understand very nicely is that with this knowledge that you are having, this is a great opportunity, because you're learning the cadence world, and what I said here with this cadence virtuoso, which is a digital world, and with a special time domain based simulation approach to electronics. And what you learned more here in this lecture is the RF world, where you tool use tools like, as I said, QUX. This is not a famous one, but it's an available one which doesn't cost any licenses, while you do either Advanced Design System or Microwave Studio. And this is really useful because you get access to these tools very early in your career. And if somebody asks you to whether you can use that, it is quite helpful, yeah, because people ask you when you are searching for a job, have you done this and this and this, yeah, and that's very, very nice. And you can, and as it takes time to learn software always a bit, get used to it, this is a very nice opportunity, and this is the world we are in. So and the lecture touches on first of all on things which we do in the frequency domain, as we will later call it. But as you know, bits, for example, they are time domain concepts. So what is a time domain concept? I don't want to be so generic already here, but it's essentially a bit is a time domain concept because it turns a current on and off over time. That's a very nice and simple concept. And you learn here to design in both worlds, and which may sound still a bit crazy, doesn't. When I give you the examples, you will understand what I'm talking about, because this is fast data communication, and this is both RF and also time domain stuff. So very interesting. And just to mention it, we are not just talking about this stuff, we are doing it. So my personal research is a lot devoted to 6G already, which we'll come to in a minute. So we do the stuff we are talking about. Here's a clean room in the backside where we are making some of the highest chips for the highest data transmission experiment on this planet. So we are talking, so think of your cell phone to receive something like 100 gigabit on the cell phone, not over the fiber. So these are things we are researching in for the future. And and this is really a domain which is rolled out by sophisticated research, and then also in the development we also make examples for that. So we build this stuff not just as chips but also as systems which, for example, so things we typically do is to transport 100 gigabit over the air from this building here to another building somewhere, maybe the IMTech or INATEC or some places nearby, and we'll come to why we are doing this. There's still a hand up. If it's a question, just speak up. So don't wait just interrupt me, because I don't see the chat live all the time. Yeah, and then there's a lot of hidden stuff which makes this lecture particularly valuable. I mean, when you talk about microwaves and talk to your friends, they normally think of the box on the top left, which is a very nice device, by the way. That's not so easy to do, but there's a lot you can learn also from that. But many of the features are related to safety, as we see on the top right. So microwaves, you have been touched by microwaves today because some car, some bike has already crossed you today, or some lorry which has caught you with a radar beam to protect you from any complicated traffic situation. Yeah, and this is by now not just this simple situation here that you are trying to avoid crashes. It's all about safety, because you can essentially build a screen of sensors around any vehicle, including bikes by now, where you can put radar. So I recently even saw a person having a radar for a bike cycling, just to, if somebody approaches from the back, that you don't miss this person. So even this exists because this stuff is a commodity. It's getting cheap, and you can essentially get safety and all kinds of features with that. And then, of course, we have the very strong development in what you have in your hands. Today, it's still called a cell phone, but it could also be a watch or something in this direction. And yeah, and maybe I'm always asking this question. Is there anybody in the room who doesn't have a cell phone? Maybe. And then maybe the question, is there anybody who has such an Apple Watch? Maybe it's interesting to see that. That's interesting. Okay, nobody is using a watch, so that's another device, because some of this stuff will be in the commodities will come around, and we never know what the next thing is going to look like. And maybe who has ridden a car or some vehicle which has had some radar function? That's also one thing I'm asking always. So who has sat in a car which has for some reason has some safety, passively or actively? There's not so many people coming up, but maybe sometimes also that you don't know that that's in the cars, because or in the vehicles you're using, because many of them have that by now, without even you noticing, and this is part of the safety concept. Yeah, so that's the RF system thing. And for the system side, I'm very clear. So microwaves is not everything, but what you can learn in microwaves very nicely, how you build systems, what is important there, rather than speaking. Maybe you say microwaves is not my first thing I'm thinking about every day, but it's very nice for thinking about systems, any kind of system, because you can gain that knowledge, and you because you are also studying this in many there's systems in your studies. Yeah, and system design itself has a many features, so that's something you can really learn something about, and that's what we want to tackle here. And that involves, of course, many things. So, for example, so in the center, when you have such a radar, you can take it from the core. So you have some central chips, which does a lot of the microwave stuff, but you need all other things. You need up and down conversion. Yeah, so we have to learn how to change ranges of frequency. That is a bit fuzzy for you, yeah. But what is really important is this data acquisition. Yeah, so that's something. So what I really want you to understand is, what does frequency have to do with bit rate? Oh, why is my cell phone so slow, and why is it not giving me or why is the internet never fast enough? Yeah, and we need all kinds of things. We need the data processing units, how to do this efficiently, and your cell phone, when you look at the architecture, is doing this particularly nicely. Yeah, so this is something you can understand, how you transfer over the air. And I have a question for you. Maybe somebody can answer that. Why are we not sending bits over the air? Just a short review. Anything which comes to your mind. Why don't we just send bits into the air directly? What goes wrong? Somebody want to try to answer that? There's nothing you can say wrong. Just go ahead. Yeah, very nice. That's a very smart answer already. Has a lot of content, which is very good. Yeah. Other thoughts? So just why is the microwave, the analog side, always needed? We can turn the question around. Why do we send stuff at one frequency or a few frequencies? Feeling for that? Yeah, very good. It's also completely correct, but maybe even simpler. So the first idea is that different frequencies, which we can use in a spectrum, we will talk about this. And if you look at my background, they're just at different frequency. All the things we have, buildings or the atmosphere, they behave differently. And as was said with the first, I think it was Frederick answer saying that, um, you you simply get, if you send one frequency, it simply propagates through the atmosphere differently than if you take two times the frequency. And if you ask yourself, why is that? Have you experienced that? That is also something you experience otherwise. Yeah, so you're not really surprised that X-ray things go through uh, through a material, while other frequency like optics are absorbed, optical frequencies. So that they just, and this is the same here. Yeah. So we have to learn what the atmosphere does with the frequencies and also what buildings um, um, do with the frequency. That's something which is very important. So, and you sitting in a room, so just imagine the room you're sitting in, and this makes already a geometry, and then you can, like a music instruments, frequencies either fit into the room or they don't fit. And then you start thinking, that seems to be reasonable. So I'm running around a building. So some frequencies or some wavelengths equivalently will be changed or will be modified in their propagation, to be more precise. So that's something you may have in the back of your mind. Yeah. Okay, let's go back to the cell phone. And here's already something um, which you have in your hands every day, but I really dare to put it on the thing. But my first question is, in your cell phone, where's the antenna? So if you look at this, have you ever thought about it? I mean, apparently, when we want to transport some frequencies or some microwaves, where could we have the antenna? Does anybody want to give a guess, or what is it? What it could it be? Where in this case which you have in your hands is the antenna? Just speak up, so as is same as if you're in a room. So, you. Yeah, okay, that's already the advanced. It's the advanced answer. Very good. Three is of course Sean. Very nice. But could it be in five? Yeah, very good. Yeah. And the answer is that is the first thing. There is an explicit antenna, but it's, as we say, conformal. Yeah, it's so in the early days you really had to have to jockey people in here still. Sorry for that. Um, you had to really take something out. Yeah? And the reason I mention this is that there is, of course, an explicit antenna. Yeah? And because we need some things which get the microwaves from the inside or from the chip, as you see, into the air. So this is something which is really important, because otherwise, if we had a cable on the cell phone, which would for connecting it, that would not be so useful. The mobile aspect is, of course, very important. Yeah, and that is also the advanced answer. Um, Number three, the answer is of course perfectly correct, but the antenna there looks very strange, because essentially the antenna there is just a flat structure with some pinpointing at some in part of the layer structure which you see. And this is something which is what you see here. Just for all of you, you have that at home, by the way, or in your hand maybe. This is already an active antenna, and it's also a smart antenna in the sense that it can change its where it's looking for the signal. We will come to that. Yeah, so that this has to do also with efficiency, because if you're sending all the signals everywhere, maybe this is not the smartest thing on earth for the power consumption of this thing. But we will come to that. So there's a lot of system thinking, especially with the stuff in your hand. Um, what do we need for this? And just to wrap you up, we need all kinds of circuits. So there's a digital part, which is of course um, um, very important. And again, I'd like to ask a question. What is the thing you look at when you buy a cell phone? Which criteria do you put on except from the price? So how do you select the cell phone? Which numbers come to your mind when you go to a shop or look at the internet? What are things which you think about and maybe not don't think about? So your latest cell phone, how did you select it apart from getting it from money-wise? Or if you had a, go ahead. Oh, in this order? Uh, Okay, very nice. Okay. Other people? What is important? What is very annoying when it goes apart from the battery? If it's what when do we typically think for the first time we need a new cell phone? Which second? Can you explain memory? Yeah, very good. And that's important. We are talking about a microwave thing, and the first thing which goes bad is a digital function. Yeah, so you're first thinking, oh, I cannot put up the apps anymore, and I've taken too many videos and pictures that the stuff is full. Yeah, so that's very weird. It's actually not logic. Yeah, because somebody said the microwave connection technology. I like that. That's very good. So but that's rather technical already. Yeah, and then the other thing is, which I liked very much, is so we also have very good processors in there, and what is where the cell phone is by now the most dominant contender is simply that it is processing power per battery life. Yeah, so in this sense, this is on a system level a very good thing. So you can of course get faster computer to do the processing, but you also have the battery in your cell in this thing which has so and so many much capacity only. So that's something which you really need to think about. And then there's a lot of things which are given here which we want to talk about, which we need as functions in order to make that happen. Yeah, so there's especially this mixed signal thing which is very important because we need to get these bits which we are somehow having on the cell phone. It's very clear that the camera output is digital, and that has to go to an analog wave. And as I said, the wave which is leaving the cell phone is analog with the digital stuff somehow on it, but we are not sending away the bits right away. That doesn't make sense. And why that was because we simply cannot transmit them. They would get wasted and we would lose the information. Yeah. And then we need a lot of things, software and especially also data processing. But that is something which is also very useful and of course a big story in this. Here I opened it's actually by now it's more from the museum. This is a very old chip, but you can still see the radar. This is a radar. So just to give you a feeling what it is, and you see there's a chip in the center, but there's all kinds of things you need. So you need to get the signals in and out. So this is this part. And the radar beam or the signal which is sent and reflected back is coming from this side here. So this is where you see these are somehow the connections. Yeah. And then you need all kinds, you see all these bond wires and all these connections. I'm showing this explicitly today. This is much more integrated, but then you don't see anything. So that's why I still have it. And you see you need to put DC in because this radar apparently consumes simple energy, and this is DC energy. Yeah. And we need a couple of ports to get the signal, which is first of all sent away and then reflected. It's somehow processed, and then at some point, typically here, you will take the data out. And then so you see it's to get a system, you need to integrate certain chips into the system, but at the same time also you need the chips, of course, but there's also an environment of that because not many of you have really seen radars maybe, but to get them useful, you need a lot more than just uh, the electronics themselves. And this is something you would like to have at home. This is a 100 gigabit optical fiber communication thing. a unit which may technically connect. Maybe if we had it for the IMTech or for the INATEC, we would be very happy, because this would mean we would have a 100 gigabit link per or even higher. And I don't think we have it yet, but it's and we also, and the point is, this is the wire line, and this is also very useful to us, because some of the stuff I'm getting to you at the moment is going via fiber. Yeah, and maybe to ask you to make the distinction again, a small survey. Why do we use fibers instead of microwaves? Why don't we use microwaves everywhere? What is the basic idea which we all fly on, so to say? I mean, the other way around, it's easy. We use microwaves because they're mobile, because you don't want to have a fiber in your pocket. That's very simple to answer. But why do we use fibers if we can? Very good. Yeah, it's a very robust way. It's safe. We'll come to that. Very nice. And the wavelengths of the light, that was something which came from the chat. Very good. Can you could you say why you or maybe write it up, why is wavelengths important? Because this is actually what we're going to look at next week already. Maxim is writing something, so let's see whether we can. He makes it known to us. There's something fundamental in it. So what is good in this light we are transmitting? Why is this useful? It is the carrier frequency of the information. Yeah, that is something we have to look at. It's not so easy to understand, but it's correct. Yeah, and the trick is, yeah, he says less interference. That's also, somebody, Pranav is saying this. Less interference. That's also good, because you can fiber is essentially guiding the light through the fiber, so it's not going everywhere, but it arrives safely at least where you want it. But even simpler, why do we use fibers? And if you could just sit back, and what is the basic reason? Why is this carrier wave important? And which is exactly the right path. Yeah, it's faster. Yeah, and maybe just for your physical understanding again, the frequency of light is much higher than the frequency of the microwaves. And then this will transport also in what we later will call capacity. Yeah, so, and for example, you can have electromagnetic waves at the frequency of the acoustics, so a few kilohertz. But what you then get in bits over this carrier frequency is rather low. It's a very fundamental idea. So the higher the carrier frequency, the better the information transport I can organize. And this is why, if we can, and maybe somebody said it, I'm just checking, it's faster, less interference. And the other thing is, what about the sky behind me? If you think in absorption or in the damping, what is very nice about a fiber in comparison to this sky behind me? Just think where we are using fibers. You can guess. So there's somebody sending a fiber over the Atlantic. Why are we doing this? Or through the Atlantic, or through the Indian Ocean, or through the Pacific? Why is that? Yeah, it's correct. And that's extremely fun. It's maybe you may find that answer which I'm giving stupid, but it's not. It's just it has to do with how much power do you have when you start, and how much power does arrive where we want to go. Yeah, and this is very significant. Yeah, And maybe some of you had that experiments. There were recently a few thunderstorms, which were very heavy rain. Yeah. And then you can see that if you have a satellite transceiver and are watching TV, if you still watch TV, I know not many people do this, but let's assume you do this kind of crazy thing. And it really happens that during a thunderstorm, the TV doesn't get any data from the satellite anymore because it has to go through the atmosphere. Yeah? And this is not always, of course, when the sun is so shiny as behind me, that's fine. But if you want to watch TV or get the data also when it's raining, this is a big problem because water, especially, it attenuates waves very strongly, and the fiber doesn't. Yeah. So that's something you can maybe already consider. We will look into very great detail with respect to that. Yeah. Okay, and this is then how it's working, and this is also part of this lecture, which we all have at home, is this idea that if you get a certain data stream in, you want to put it to the highest data rate we can get, and then you want to send it over an optical fiber. Maybe in our case here, we are on the south link here. Our main connection is to Karlsruhe, and the next big hub is then towards Zurich, and then this is the connection. How we will look at this map of the fiber network for Europe, that you get some feeling about this. Yeah. And then you also have to take that data out again. That's something, not everything you send is also being received, and we will have to talk about how this works in particular. I was promising some system stuff, um, but maybe we can also talk about that. So that's the most crazy stuff we can at the moment get. It's not so crazy actually because you're using it every day. So for example, where this is particularly important at the moment is when you're connecting the cloud. Yeah. So the data centers, which is what you receive as the cloud. Yeah. And you could see it. It was in the news last year that somebody. So let me first explain what you're seeing here. You're seeing the optical data link between the cloud servers making up a social media network. Yeah. And they are presently doing this exchange of the hardware where the servers are on the different places on the planet at a speed between 400 and 800 gigabit per second. Yeah. And you could see that this was wrong because there was at one point this old-fashioned organization called Facebook had a problem with the coordination software of those controllers here. Yeah? So the controllers, they put in a new software, and suddenly those links were not in sync anymore. So Facebook essentially crashed. Yeah. And that's the data center idea. And this is extremely important because if those servers have to be running, they have to be fast. And this is exactly when you access any type of service of this kind. It only works if they can do this specific high data connections, first of all, towards you, but that's not the only thing. This is what is really the hardware behind Facebook or behind any social media application that you consider. Yeah. So this is really vital. Yeah. And then there's another point, and before we go to that, I would like to ask a question. Have you ever had the feeling in your life that the internet was too fast? Any moment in your life where you had that thought? So this is typical. So turn it around. Who has thought that the internet is not fast enough? Today I nearly got crazy to transmit a 100 megabyte file. So we have a majority here. And maybe we make a survey. What do you think is making the internet slow? Where in the network does it go bad? Just speak up. Don't just mention it. Why is it slow? Any ideas? So, yeah, go ahead. Yeah, very good. Thank you. There's multiple users. This was also said. I like that. This is very, very good. And limited data due to frequency. That's nice. Very good. That's perfectly correct. But first of all, do you have a feeling which components are limiting? So it's a sequential system. It's a parallel system also, but it's a sequential system. First of all, why are we limited at all? So which components in which you are using? Is it your cell phone which is not good enough, or your computer, or what is limiting? Bandwidth, yeah, very good. And which component is bandwidth limited? The router. Yeah, maybe, but I think the Inatec still has a good the transmitter and receiver. That's also a nice idea. But we are not coming to the point really, and it's difficult to say. I can only say statistically, the channel, that's good. And the idea which we are facing is that this idea that it's a sequential system. So even if all the things you have in your hands are fast, and you know your WLAN which you're using can have 800 megabit, a gigabit, or even your computer can have very wideband connections, but it's not so often that you really get a gigabit, because somewhere in this stupid system something goes wrong. Oh my God. Okay. That was perfectly rehearsed, because when I said wrong, the internet crashed. Can you hear me again? No, it's important because I had a full crash of my system. And it was exact timing, and it didn't plan it. So just to be very clear. So let's see whether we lost other people. We are now 18. Let's see, is anybody? So you're still there. That's good. And just coming back to the lecture, very clearly, there's components which are always too too slow. And let me just share this again correctly on the Teams. Let me just get this, and I will use this one. Okay. So here is the wireless links, and there's some guys or some components which are always limiting, and it's typically the point-to-point links. Yeah, so this idea which all of you had is very good. So we are collecting this data from the microwaves in a base station somewhere, and then this has to be fed into the internet, whatever which is typically then, which we call then the MetroNet, which is then getting to the wide area ranges. So there's always this idea, we have the close proximity. There's something what we call metro. That could, for example, be a ring of fibers here in Freiburg, and then at some point it goes into the open side of the rest of Germany or Switzerland or France. Yeah, so that's and these links are typically limited, and then the arguments apply which you had, which are that the bandwidth of those is limited, and that has to do with the frequency. Yeah, so this is very correct. Yeah. But systems is not everything. Yeah, so there's also some other things we have to consider. So here I was going for maximum performance. Yeah, that's also something which so here we are asking, the internet has to be fast and whatever, and very, very agile and very available. Yeah. But what you need to do in systems is also maybe things of some other properties. So it's not just about performance. It's also what we have here. And one of the reasons why we are talking about this is this major catastrophe here at the in the Ahrtal, which is seen from you. It's in the middle of Germany, and there was a big flooding, which essentially killed all the infrastructure based on a sudden rise of the water in a very shallow and very small valley, which made a river which normally had something like 40 centimeters in depth actually rise to 12 meters in shortly. And the point is, which I'm trying to make, is we are very bound to this maximum performance. So we think that Facebook has to be available, and all these networks. But what happens if the infrastructure dies? Yeah? So what happened there was essentially that only by real chance some communication stuff remained, so that the emergency forces were able to connect at least to some extent, but many places even didn't have connection for days. And that is also just to remind you, uh, people don't do internet for a day or so, and they consider that reasonable, but because it's healthy for you, of course, maybe mentally. But the point I'm trying to make is, can we live in many ways in public without this data connection? And what you learn, of course, not only due to the disaster here, you learn that this is probably critical. So, and then even in this thinking, you how long do you need to rebuild this? So and this is here already a time, weeks and months afterwards, that you learn, if you don't have it for hours, you are not happy, and for emergency, even minutes count. But you also have to think from the system side, not just from the availability, but also from the availability when something happens. Not only the positive case, but just, for example, just this idea, we are discussing this also at the moment. If we had short power failures, how long would the mobile communications base stations remain online? And the simple answer is not very long, because the batteries you have in these systems, there are some batteries in there, but they will probably be down in ranges like hours rather than days. So that's something. And this is, of course, yet now a very specific case, and it's also a major catastrophe. So I don't want to go back to it, but you learn something from the system side. So what do you design a system for? And for example, you could take your laptop. In the case of your laptop, it's very clear. If you don't have a charger and no current, you can run for some time, at least individually. If there's network, you even get a connection, but if the network is not there, then you're stuck. And that's something which is getting, which it's very fashionable, but has already been talked through a lot of times. And especially this idea that we get so dependent on the story is a system thing, which we have to think about. So what still works if you don't have power, if you don't have internet, if you don't have landline communication? That is something which of course from a system design has also to be incorporated, and we are thinking about that. The other way of looking at this, because this was the resilience aspect, the other aspect is how much um, energy does all this cost? And that's something I'm researching in today. Um, let's make a pool again. Some company told the people not to charge their cell phones at work. Is this a meaningful energy saving? What do you think? So can the company save money if the people are not charging their cell phones at work? Any comments from your side? Does this make sense or doesn't it make sense? But let's put it in cents or in euros. How many cents can the company save even if the price per kilowatt hour is very high? What do you guess? Is this meaningful? I agree. This is an easy question because it's easy to calculate. If you look to the battery of your cell phone, it can do a couple of amps when you check it, and it has a capacity and it does a couple of volts. So simple equations say that current times voltage is power, and um, you get from this you can deduce this is maybe some watts or some watt hours which you save there. And even if you have 1,000 people, so what to look at? So it went through the news. So you are students and you can think. So it's always good that you start thinking and make some guesses on numbers. Not everything which you're being told is in the news is useful, but the point is when we do this, we miss, of course, something. For example, this is here an energy perspective to 5G, which is the present mobile communication service. And what we need to learn is that we are spending a lot of energy not because we are charging the cell phone, but because we are causing things to do something for us, which we don't even consider. We ask for it very, very abstractly. So, for example, we ask the cloud to back up for us. So that's a very strong idea. The cloud will be safe, not from an IT perspective, but from a perspective it will be available. Yeah, and for this already uh, we'll put in a lot of energy for this backup. Yeah, so that's something which is very, very critical from our requirements. Yeah, so the other thing is, for example, that when as you saw, we are starting to use very complex systems and services in the backbone. Yeah, so alone that some transmitter feeds all this microwave information for whole Freiburg or for whole Baden-Württemberg or Germany or Europe is a major requirement. Yeah, and that is something which I would like to say. So the indirect costs of the things we are using are way higher than the direct things. And already, and for example, for the direct microwave part, the one which for the charging, which we do ourselves, this is relatively moderate. But the big story comes when we look at this network. Yeah. So the network is the big power hungry story. And one reason why this is so power hungry is because for reasons which have to do a lot with this, they're always on. Even if you are sleeping, not looking at your cell phone, they're always available. Yeah, and that is probably one of the biggest failures of the internet, that it's so available. Yeah, because it always assumes that many of us wake up or are available, and that they actually provide this maximum performance of the server systems. Yeah, and we have very little control. So normally you would say at night when I'm sleeping, you don't need this, but the internet from its fundamental definition is really a system which is always there, always on, and always assumes you're using maximum performance. We are only now learning to turn it off a bit in a positive way. So it's not about turning it down, it's turning some capacity off in the sense of saving some energy now that energy also gets more to our understanding. Yeah. So that's something which I really would like to um, mention here. Yeah. So just a few items about what we are talking about here. So one thing you should learn is that some people still think when you ask, you are not thinking this, but some people do, that cell phones talk to each other. Yeah. And that is true, but only via a network. So it's always an access system. Yeah. So you can have an access service, for example, like this one, which is a typical base station scenario, that you say there's several users like you in this room, yeah, and you're talking to one WLAN or one base station, yeah. And then the data is aggregated here and then sent to another access point. This is then called the mobile service, for example, and then sent again to other users. Yeah. When are we using direct communication of cell phone? Which application does use direct communication between cell phones? Does somebody, there's a few, but can somebody maybe name this? When do cell phones talk directly? Yeah, good. And which other one? When do we typically use this very direct talk from one cell phone to the other? There's one thing where we really want this, and you have to enable it to do it typically for safety reasons. So remember what you did. If you had a cell phone and you're getting a new one, what do you do typically then? There, NFC is the correct answer. You may not heard it as NFC, but I'm sure all of you have done this. You put cell phones on top of each other and make a direct connection, near field communication. Yeah? And this is a very smart idea, by the way, because in this sense, what we hope is that at this moment, the only cell phone number one talks to cell phone number two, and the data doesn't get anywhere. Yeah, which is for backups, for example, a nice thing. So we would like to have that more. So, for example, if you could put your cell phone at night, for example, to something, and it would back it up automatically, that would be a feature which we may like. Yeah, so it's you can have that in some services, but this direct communication to something is a very nice feature, which sometimes can be really useful. Yeah. But in general, this is not the case. We have an access-driven network. Yeah. And here, for example, here you see already some examples. This is not so surprising that I'm talking about Wi-Fi or WLAN, wireless local area networks. And this is also a very interesting technology because it has many things which you would be surprised it has. Yeah. So, for example, the WLAN is, for example, a service which from the beginning has worked at two frequencies. Yeah. And maybe as a starting point from the audience, what could be a typical frequency of Wi-Fi, just in gigahertz, roughly? I think you have seen those whenever you did this. What is Wi-Fi using in frequencies? Yeah, and always has. Very good. Yeah, and you know the 5.1 there maybe you have seen this already. When you're using the 5.1s, you know this is probably faster. There's two reasons. Not everybody is using 5, and there's also more bandwidth in this. So this is where because the nice thing about micro is you know a lot of things without having thought about it. That's what I'm tracking here. Ne? And does anybody in this room have such a router which looks like this or similar? And my first question is, why does it have these three antenna? Why does it have these? They don't have it yet so often. So the first ones didn't have these, but the more advanced ones have these. Why is this? Why do they have three antennas or four or sometimes even higher? What is the reason? And this is quite simple because you're looking at me and you see my two ears. Yeah. Yeah, tuned for different frequencies. Yannick, this would be nice, but unfortunately, this is really not the case. Yeah, both antenna, all the three antennas, I think they're covering both frequencies of use. Yeah. It's a good idea, but this is, in this case, it's the same thing as my ears. Yeah, my left ear and my right ear have the same frequency range where I can hear. Yeah, and now you can say MIMO, this is something very advanced, but before we come to MIMO, just to get this idea, something you know that with your ears, you can track somebody down behind you. So you know where he and she is. Yeah. And in a way you could say that our brain is doing some kind of this MIMO, because the essential idea is that, as a first idea, you say there's a difference of the phase of the signal if the person is left of you, because to my one ear the distance is a bit shorter than to my other ear. Yeah, that would be in a very simple way. And the other thing is that is also something you can check, that the signal is not only coming in one way to me. Yeah. So, for example, for example, consider the situation: you are standing, there's some radiator, and then you're standing behind the building with respect to this transmitter. Does the signal come from the left, or does it come from the right around the building? And the answer is both. And you can make use of this information, because smart receivers, they check what is the best path to get the signal to you. Yeah. And why is this useful? Because you all know that when you're in a room, there's spaces where there's better connection and there's spaces where there's worse connection. Yeah. And the first thing what these antennas do is to point by phase difference to certain regions of the building. So if you're walking around with your cell phone in a house or something, or just moving relatively towards this router, if you would send it everywhere, that's smart, but that's not very energy efficient and also not very cool, because you're always then you send it everywhere. You can see it's sent everywhere, but only a small part of the signal actually gets to where you really are. So this is not really an efficient way of doing it. So this phase different sends something to you, but also listens to you, because if you have to listen to all the environmental things all the time, to every angle around this antenna, that's not so good. Yeah, and especially for the higher data rates, and this is why it only came up recently, it is easier to organize if you know somehow where relatively to the router your cell phone is. Yeah. So that is what even such a simple system, this is actually quite an advanced concept, but even the simple Wi-Fi does this. And again, it's an access system, yeah. So that's just to give you this idea, and it's also, of course, a system which is relatively powerful, yeah. So we now get gigabits over the Wi-Fi, and this is also not just a cheap technology, but the technical advancement there is very strong. Although it's just WLAN, yeah, but just Wi-Fi. That's but you need it, and it's getting much better, and it's increasing strongly in data rate. Yeah, so that's here you see that with the chipsets. These are some early diagrams. You see this is made for the frequency of 2.4, which was mentioned, and 5. Yeah, so and which means that you need everything double. You need the transceivers for each frequency. We will come to why. Yeah, and there's a different antenna. Somebody proposed you need a different antenna for a different frequency, which is correct. Yeah, but we will see why that it's possible, and this is actually something which is against nature a bit, because somebody said when we talked about this is where's the antenna? Yeah. One rule in microwave is that the antenna should always have some relation in length to the wavelength. Yeah. So if you have a simple dipole, then you know from basic physics experiments that the length of the dipole has some multiples of some wavelength. Yeah. So maybe fits in 3 times or 4 times, that is a good antenna. In this building, in this device, people built some very advanced forms of antenna, which are not easy to calculate, where you make it frequency and wavelength independent, so to say, that you design a geometry which by very high engineering skills is possible, that you build something which is not having this relation. Yeah, so you build an antenna which works for 2.4 and for 5, because this is what the Wi-Fi antenna does. This is also a Wi-Fi antenna, and it's even good at these frequencies. Yeah, so that's something. So this simple intuition which you had from the physics that this thing has to be as long as the wavelength is, this is here a bit omitted. So in this sense, your cell phone, because it has to be stylish. Yeah, so think of a cell phone where you have to take out an antenna. This is because of the stylishness that some people invested into the engineering, although it's not maybe the easiest way to do. I have a question for you. What is 2.4 gigahertz in wavelength? Just if you don't know it, guess what it is. What is that? Is this kilometers, meters, decimeters, millimeters? Just try. It's not bad if you. Or how would you calculate it? Maybe this is an idea. Yeah. So the simple idea is that um, the 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 product of wavelength and frequency is a constant, as said there, and it's the speed of light. Yeah. And one thing which you have to learn, and that's important, um, why do we often give frequencies and why don't we give wavelength? There's some fundamental differences between, if this is the case, the product is a constant. What is the problem? Or maybe somebody can say, why do we buy frequencies? Why does Deutsche Telekom buy frequencies, but why don't they buy wavelengths? There's a very fundamental reason for doing that. Have you ever thought about that when it was in the news? Deutsche Telekom had to buy 50 million euros for the frequencies of 2.7 gigahertz or 3 point something. Why do they buy frequencies? It's very simple. If you had to buy them for the Deutsche Telekom, which you may do some days, why would you buy frequencies? It's very simple because frequencies never change. Frequencies are unique. Yeah. So that's something which you should take home from here. Deutsche Telekom or Vodafone or British Telecom or Spring in the US or an Indian company or an Australian company or a Japanese company, they all buy frequencies because then you get frequencies are never changing. Wavelength, they do change. Wavelengths are material dependent. That's very important. Wavelengths are changing. Yeah. And that's a bit, so that's something you can learn, and you really have to know that because you know it already, because when you say, they said they bought some megahertz somewhere, they didn't say they bought the decimeter band or the centimeter band. You have never heard that part. Yeah. And that already tells you something, and it's also a very important message that the wavelengths for some reason are always in relation to the devices we use. Yeah. So for example, for the cell phone, I'm sorry, there's confusion here. For the cell phones we are using, you can actually guess what it is. So the cell phone is a device which is transmitting typically at the moment between 0 and 6 gigahertz. So take 3 gigahertz, and it is 10 centimeters long. And this product by accident is the speed of light. Yeah, so this is easy to remember. So it's 3 gigahertz, roughly, because you know that the speed of light is 3 times 10 to the 8 centimeters per second. Yeah, it's exactly what we just said. Yeah, and the wavelength emitted by the 3 gigahertz in air is a decimeter wave. Yeah, 10 centimeters. if you apply a typical material like plastics, which modifies, which is what we learn later, then the wavelength gets down. Yeah, so the wavelength always gets smaller when you are entering materials, and that also means that then the speed of light in the material will go down. Yeah, so it's a very practical thing to remember. Yeah, so it's not something which is difficult. Okay, and then there's also concepts behind this. So here you see again our MIMO, and the idea was, which was said earlier, this is also a system concept now, is that we said already we have many people in this room who need capacity. So the capacity adds up. So if everybody of us gets 1 gigabit per second, we are 18 people in this room, so we need 18 gigabit per second. Yeah? And the point is now, the moment if you're in a fiber, that's relatively simple to organize, because then there's an input and an output of the fiber, where we do this. This is relatively simple, but 18 people running around is not so easy to organize. Yeah, so running around the router. So in this case, we use this MIMO to find out where around relative to the router these 18 people are, because then we start sending the information only in these angles relative to the router where the people are. Yeah, and it's not a very precise tracking. So I just want to tell you that, because with 3 antennae, the tracking you can actually do is not very good. But you can at least say, is the person on this side of the antenna or on the other side? Or maybe the angle in space is already reduced. Yeah, so you're not wasting your resources on sending it everywhere. Yeah, and it's not only for transmission. The main reason is also that because you're also talking to this thing. When you're getting away from this is a very efficient way of keeping you above the noise floor, which is the limit. So if your signal is getting too weak relatively to the router, yeah, so you're going away further from the router, or you're talking um, relatively with a low volume, if you take that analogy, then the router will use this system concept to search for you only where you are. Yeah, so if you know the person is on the other side, then I only will listen to him or her there. Yeah, and that is a smart idea because it's like pointing and you check where is the person. Yeah, and the second aspect of this MIMO is that because the signal reaches you not just only straight line, so it's not necessarily a straight direct, as we say, line of sight communication. Yeah, so you don't have the nice thing about microwaves is you don't have to see the router to get connection. And you know this. You have been in buildings where the router was somewhere and there's no line of sight. Yeah, so there's simply no way you can get directly to the router with your transmitter. And then there are multiple ways of that, because it's reflected at the top edge of the building and of the room, and maybe just below, and so the signal reaches the router over multiple paths. And this is a second source for tracking you, because then with this information, this is multiple input, multiple output. This is the information which is then used to organize the network just from, and you know this is not really surprising. You know that you don't have to stand in front of the router. It can be around the corner, or there can be a door shut, or whatever you do. And there's many ways how this can be reached. And if the system is good enough, it will always search for the best connection. Just this is how networks start to work. And then there's some other surprises, which I also typically like talking about. There's the most powerful radio unit you have in your home is this. Yeah. And it's again from Notion, which you have, or which you can easily acquire. Yeah? So we said earlier that the mobile communication typically is around 3 gigahertz or lower, by now a bit higher. And this DVB-S, this broadcasting satellite, which is the typical TV we have at the moment, so the SATCOM stuff, which comes down as broadcast, yeah, this is extremely powerful. Yeah, so for these, I don't watch much TV, but I'm always astonished that people have so many pixels on their TV sets, these big things. And that means they need a relatively high data rate to feed them. Yeah? And this works because the SATCOM stuff comes down at, for typical broadcast TV, at 11 gigahertz. Yeah? And you can get a very high data rate. So you can get 1 gigabit and more of information received due to that. Yeah? There's a problem with this a bit. This is not, as we say, duplex communication. So it's just one way. So you're just getting something, but you're not talking to the TV station back. Yeah? So you just get. Yeah? This is broadcast. So somebody is in space and sends the stuff down on Europe or Germany, or as given here, the United States. And this is how you get vast amounts of data in one way towards the people. Yeah? And but it's a channel, and it's a very powerful channel. Yeah, so that's just something I wanted to mention, because the best serving, apart from if you have a fiber at home, that probably would be equivalent, but this is, at least in one way, a very powerful radio link which you have. And here is the principle. So there's the satellite, and then there's of course a lot to be involved. And what makes it so interesting is that for this relatively high data rate, you also have to get the analog to digital conversion. That's why it's mentioned, because you have all this data, and what you have to think about, you have to get it in bits to the pixels. And that means that also this part of the SATCOM receiver which you have is scaling further with the number of pixels you have on the TV. So that's not, it's a relatively powerful thing which we are buying for a couple of euros. Yeah. Okay, maybe I skip that. Then there's some things which are also useful, medical. Who has had this, an NMR, and why? When do you get this? I'm not after your medical history, sorry, but when is a typical situation when you have something like that, when you have such a medical investigation? And what does this have to do with what we discussed already? It's very good. It's very good. And now we have to, maybe we explain it a bit further. Everything you said is perfectly correct. The question is, why do people this? But what does it have to do with the lecture? It's a question not directly to you. If somebody wants to say something, which part of our body has to do something with microwaves? That's quite surprising. But so first of all, what happens with microwaves inside the body? So, for example, there's just a simple idea. Can I talk to my, if I had a heart accelerating device, so such a sounder which would make my heart beat regularly if I had that heart problem, could I radiate into my body with microwaves? Why? There's a simple experience I'm sure you made. How do you know this? Why do we all know that microwaves do not go well into the body? Think of the microwave oven, and you put that chicken or what? Sorry, if you're vegetarian, I don't want to, but let's assume you eat chicken or any meat, and why do you put it in there? Yeah, very good. The body is high in water, and what does it mean? Exactly. In the beginning, the chicken will absorb the microwaves near the surface, and only after some time, due to thermal conduction, also the core will get some of this uh, energy. Yeah, which means that typically tissue, as you said correctly, is absorbing like hell, very strongly. So in the first millimeters of the body, which is good in a way, yeah, which protects us. So you cannot really well talk to inside the body. So this idea, you have some medical device and you talk internally, that only works for very specific frequencies at very low typically. And there the absorption is okay. Yeah. And there is the absorption is so okay that you don't first fry the patient before you cure him or her. Yeah, that's the problem. So if you want to do that with a high amount of power, that's not a good idea. But for medical things, there's another application which is quite nice, which is related to the frequencies. The microwave frequencies are related to the nuclear spins. Yeah. And which problem are we trying to solve? The first problem is that when you sense, when you want to see something in the body, you do not see much. However, there are cells in there, and the nuclear spins, they of course are different for different materials. Yeah. And for example, if you look at that picture, if you had an X-ray of X-ray um, going through the body, what would you see? Which parts of the body can you see well with an X-ray? I think you know this pretty well. And which things you can't typically see? That's something I think you know from your medical experience. So I think all of us had an X-ray, and what do you see is the bones, as said correctly. Yeah? But where do we have problems in seeing it, because it's nearly the same tissue as the rest of the body? That is, for example, if we have all the lineages or the any problem in tissue which is made here, for example, in your knee, at your foot, typically after sport accidents and so on. And you said brain, which is the same. So brain, from a microwave perspective, is a very similar matter. So you don't see much unless you use the spin information, the nuclear spin information. And what you can do is, with a strong magnetic field, you can make the spins of the nuclei, which are from different materials, you can make them resonate due to the strong magnetic field. You can check this change. And this is the principle of nuclear magnetoresonance. Yeah, so different materials, for example, here you see all the organs inside the body. If you put a very strong magnetic field, and then in combination with a relatively sensitive detection device of these individual frequencies, yeah, then you can create an image, because you can, looking with similar principles we had already, you can first spatially and then also by the properties, you can actually create an image. Yeah. And this can be done quite nicely. And as I said, the trick is, of course, to get weak signals out. Yeah. Because you don't want to fry the patient. You don't want to put a lot of energy in there. And the other thing is, of course, you want to resolve something. So you can see, for example, the NMR image of a tomato. So it's not an optical image; it's an NMR image, because you see the difference of this is, how tomatoes look like. This is water, and this is a bit of texture. That's what you can see. You see also some more solid matter, which is then clearly visible because it's distinct, but you also see the differences. And what you have to detect them is very weak signals. And that's why you have to build receivers which are very sensitive, yeah, because the more sensitive you can detect different frequencies, the better. So this is essentially the idea of what you can see. The trick is, of course, when you have to do that, you have to apply weak signals, and that's why we can detect them at all. You have to put the receivers. They have to be sensitive, and that's why they're typically also cooled. Yeah, so this is why you put them to such a. This is essentially a big fridge with a high magnetic field. Yeah, so it's not cool inside, but the both the magnets are cooled and sometimes also the receivers to get the sensitivity up. Yeah, and you can get a very nice physical situation. But if you have ever been in this, it's not nice. Yeah, but you have to get close. So what happens is that you put the magnetic field when it's moved around. You can it's going around you because you have to get relatively close. Yeah, but at the same time, this is a very unpleasant situation. And what people do now, they put these receivers as helmet. This is, for example, an IMTEC project where this was built, where you put the receivers very close. And for example, a child would never stay in that tube. Yeah. But so you, for a child, you can put up such a helmet, and then you can do the same brain thing which you want to do. And it is also very typical for what we had earlier. It's an array, yeah, because again, you're not you use different point sources, so to say. So you're not in this case. You're putting the receiver and move it around to detect the signal from various positions and detect the data. What you can also do is you detect the same signal coming from inside the brain at various spots, which is equivalent of running a big thing around the person. Yeah. So that is quite helpful and is also for more human reasons, reason why people look at this. Yeah. Yeah, and then I don't want to spend too much of your time, but maybe a last thing which we have used a lot, this is also interesting, is this tagging. Yeah? So what we are doing here is this is a passive receiver. Essentially, you're sending some information to a passive circuit. This doesn't have a battery. It's typically some maybe printed on a foil. Yeah, does have some minor electronics, and then you can actually see what this is because it activates. So there's an active part which is outside and powered, and then there's the tag, which is essentially a passive receiver which gets a bit of activation through the sending of the signal, and gives also some information based on being powered what it is, for example. The trick is here, of course, you have to make it cheap because it could contain, for example, the information when was the milk processed and when was it put to the bottle. But as you see, this is typically done for a bit more intelligent things or more highly valuable things in logistics. Yeah. So if you want to put more information in, then also the device typically is a bit more expensive. And for a bottle of milk, that's costs about €1. So this thing, the tag, has to cost less than a cent. Yeah. And then you see that putting information in such a tag is already critical because it's very expensive to produce such a tag in relation to the milk bottle. Yeah. So that's maybe also some idea. And here you can see, for example, how you play this. So this is the intelligence is typically in the sender, yeah, and then this is the antenna where the signal is emitted, and then of course you can here this is just the capacitance values that you apply to such a fabricated device to put it up, and then the tag is essentially emitting something, and then it's just either some kind of totally passive device which just has a signature, yeah, of some way, or you say it has a bit of electronics inside that it also powers up and gets something back. So based on the activation, yeah. So that's a principle. Yeah, and last not least is the sensors. I spent too much time talking, but it's not bad because we already challenged a couple of items. The Google car, which you have seen walking around, and maybe some of you have seen it. There's the Google car which collects the data of our houses, and there's the Google car which runs around autonomously. And what what is the first encounter we have here is that we have a distinction between microwaves and optical beams. And maybe we can make again a short survey. When is optical stuff useful? And when there's things where you know that microwaves might be useful. When do we like optics in your daily life? What could be a good point to use optics, and when does optics also fail? It's quite easy. Why do we? Yeah, go ahead. Yeah, very nice. Good. And but even simpler, if you look out of the window before we close now, why do we like optics? And what is the problem? So when you see the sky, what do you see? You see a blue sky like behind me, and then what else do you see? Very simple, clouds. And what is the problem about clouds when you think of an autonomous car? That's not so good because if you to make it a bit shorter, maybe you're also a bit tired. Um, if you have a car which is supposed to run always, and there's clouds, it means that there are certain times of the day when you have fog or clouds, which is the same, that you simply the car is blind because it cannot see um, through the through the cloud. Yeah, so you need something in addition to make sure that the car sees something. Yeah. And the Google car is actually one device which is mostly optical. Yeah, so it mainly is a camera because it's good. And like us driving, we use the optical information, but it's also good to have an additional radar because then you make sure that even through a cloud or some fog or some problems or some non-line of sight situations, you can actually see through something. And that's why we make a sensor fusion. Yeah, so we put both radar and lidar. Yeah, and that's why radar are particularly important. Yeah, and as we said, I will give you a short update for next week. So the idea is there's again this relation between wavelength and objects. Yeah, and if we want to see details with radar, we need to go high in frequency because decimeter, if you want to track the back of a car, decimeter is quite coarse. Yeah. So you want to see things, and I just want to give you one example where you see this situation. For example, this could be Freiburg, yeah. And when you have to see this person through fog, you see that there's not so much you can actually detect, yeah. Especially if you're behind the bike and you just have a very small cross section of the person, yeah. And the other idea is that we have to be able to detect also people which have a low cross section. Yeah, so especially when this is a radar thing. So for example, there's a small radar. That's why I asked earlier. In typical mirrors of normal new cars, so very cheap cars, they typically have that now that there's a 24 gigahertz radar in here which will detect this driver. You get then a light sign. And I think if any of you has used a recent new car, this has this feature also in a very in the lowest classes of the cars we can buy today. This is in because it's so useful because you can avoid a lot of accidents, and the radar sensor is also cheap. It comes down to few euros. It's not an advanced system anymore. The point is that it needs to track down um, the information. Yeah, and the reason, and what is the information? The information has to be relatively fine because we want to see the position of this person in some way. Yeah, it has, because we also need to understand whether the person is moving towards us or away from us. It's not enough that first of all, we want to see there is something, but for example, this situation could also be a false alarm, because if the person is there but stays there, then it will not shoot a warning for this car here. You may understand that. So if this is just running at the same pace or even slowing down, then you don't have to create an emergency warning. Yeah. So just as an idea. So for sensing, we make use of the wavelength and the frequencies again to get detection. That is what I wanted to get across. Yeah. And somebody said it's not faster, the Google car, but for optics, because we have a much smaller wavelength, we can see a lot more because we get many more details. Yeah. So this way, that's also a reason why we use LiDAR, or the principle of radar with light, which is LiDAR. And then you simply get a higher resolution in space. Yeah. So that's just as a first idea. Okay. I just want to stop here for all those coming late. So next time, no live lecture. What I will do is I will for the few things which are relatively simple to understand, I will run up a short video, and we will then repeat this thing later in the term with a live presence meeting also again. So I will not skip any lecture. I just have to move this one to another point. And again, sorry for not being here in the first round, but I was forced to do that. It's not my choice, but I will be in presence then as we discussed. So next time, no live thing in the room. First live thing, November 2nd, 1400, and then we can also interact as normal. Other questions? Anything you would like to ask now? Yeah, I will open this. No, I will open this. I didn't. I will open. I checked that, and there was a question for both Ilias, so you can get into Ilias. Should be no problem. And if I see this, there has to be a limit from the beginning, and normally it's not a problem. But I will open this. It's no problem. Okay. Yeah. Yeah. Okay. Any other question? Yeah. Yeah, and now we normally had orals, and last time we wrote a clausura, which then also sank a bit in the average, and people were a bit disappointed. But the reason was that the initial citing of the excess of the exam was that last time we had 65 people in the course, and I cannot make 65 individual exams. This simply kills me. You can understand that. I hope you can. And then at some level we change to a clausura. But I think in this case, if it's like the last terms around 20, I think it was a past COVID thing that we had so many people in the lecture, which then didn't show up for the exam. But if it's back to normal, I'm happy because I like talking to you. Because then I also get a feeling, okay, this arrived in your brain and some other things didn't. And then I also start thinking, oh, my presentation was bad. So that's why I like oral exams, because I get a lot of feedback from you without, yeah. So I hope you understand. For Erasmus, I think that we found the problem is for all the normal people in this room, there are very clear rules. For Erasmus, there are a lot of exceptions because our people going to other countries also get these exceptions. So for Erasmus, there's hope. We can do either. Online is a bit critical, because under normal circumstances, online from remote is not so nice, because then you have to be at some room with some other person. We'll find a solution. Just mention it to me at some point and we will find something. Yeah. I hope this helps. So we can either go earlier after the thing, or we can. It has happened, yeah. So there's many, but it's only for Erasmus. Not that everyone asks for an individual date. It's just for Erasmus because we are so polite to everyone because you're being received the same way in the abroad. So that's the idea. And there's different rules for Erasmus. Okay. Any other organizational things you were not sure about? No, somebody not having access to something. Yeah, everything. I always make it recordable. Yeah, but I like also people being there. So it's very bad if there's nobody showing up because me talking to a wall is not fun. You can so teaching in electronically is as painful as listening to me. So it's full duplex. Yeah. So, but I will record it always. I always did record, even prior to Corona. Yeah. And the reason is you have busy schedules and they are bad and you are overloaded. We know this, and so it's your choice. But I appreciate people being there because my feeling is you learn simply more when you discuss and interact. Okay, but now really want to close. I don't want to take too much of your time. Thanks a lot. You can always write emails. You find me on the net if there's any uncertainty, and I will need a couple of minutes just to let you all in for the Elias and also for the his. So check tomorrow morning, then it's safe that everybody will be in. Okay? Appreciate it. Thank you very much. Bye.